let me tell you a little bit about our speaker for today. So I'm really excited to have on Javier Ideami, who is what you might call a multidisciplinary multidisciplinist, who's done just a wide variety of work in a wide variety of fields, both scientific, artistic, political, lots of places. And one of those things that he worked on is something that's really near and dear to my heart, which is the landscapes of the losses of neural networks. That is the shape of the loss function that we normally only get to see in the form of gradients or a few tiny glimpses. This really cool way of getting to see it in greater detail. And so it's an amazing project. It's a ton of fun to both to play around with and to learn a lot about neural networks. And he'll be talking about it today. So without any further ado, let me hand it over to Javier.
Thank you very much, Charles, for the introduction, and thank you to Weights and Biases for inviting me to give this talk. It's really exciting, and also very excited that you've done your PhD also in a similar area, so this is super exciting. All right, so I'm going to speak about the Lost Landscape project. So what I'm going to do is, over a few minutes, I'm going to speak a bit about the context of it all. Then I'm going to take some minutes to speak about the dynamics of these landscapes in movement. That is really fascinating. And then I'm going to show a 10-minute video with many examples of the project. And I'm going to speak over the video describing what we see. And I will end up talking a little bit about the Lost Landscape Explorer app that I just released a few days ago. As Charles said, my background, the background of this project is multidisciplinary, and like my background, there is a combination of engineering, technical fields, many creative fields. And so what are we doing in the Lost Landscape project? So we care, of course, very much, right, about the performance of our neural networks, and we measure that performance with the loss functions. And these loss functions are comparing what we are obtaining and the target that we want to obtain. And this way we get the loss value, and we use backpropagation, and we change the weights of the network. And of course, the loss function depends on these weights, and we may have millions or billions and very soon trillions of weights. So these are very high dimensional and nonlinear functions. And of course, we can use different types of loss functions depending on the objective of what we're doing. If we're doing a regression, classification, we're working with GANs. But the objective is always the same. We are trying to push this loss value as small as possible, of course, in different ways, depending on the constraints and the needs of whatever we're doing. And so it would be really interesting for us to understand what is going on in all of this complexity, on all of these complex weight spaces, and to tackle this challenge, numerical analysis and visualization complement each other, and they are partners that work together. And working together, they can help us understand through understanding these complex high dimensional spaces, more about how generalization works, ways to improve our architectures and our optimization algorithms, etc., etc. And we all know the importance and the usefulness of visualization, because visualization complements numerical analysis, but it deals with information in a different way, and it gives us a very unique and different perspective on things. That's why, for example, Einstein used to mainly use visualization, and when he was chasing new insights, for example, imagining that he was a photon traveling through space, one of the many visualizations he used to get to his theory of relativity. And on the right, we can see the first picture of a black hole that was released recently, and that may eventually one day earn a Nobel Prize. And these visualizations, what Einstein used to imagine, and the picture of the black hole, and the representations that we will see of the lost landscapes, they are big simplifications of that underlying complexity and reality, and yet they are so important. Why is this? Because when we are dealing with things and with complexities that are so unreachable, so far away from our reality, like the black hole, like what Einstein was dealing with, or like these lost landscapes, like these very high dimensional spaces with billions of dimensions, even these very simple cross sections, simplifications, can be the key that take us to very unique insights. But the important question that we always have to do, either with the imagination of Einstein or the picture of the black hole of these representations that we will see of the lost landscapes, is are they capturing at least some important connection that provides useful and actionable data? And we will see that with these lost landscape representations, the answer is yes, and we will explain why very soon. But so, our challenge is that we're a little speck of dust in this big chart of the amount of dimensions that we can deal with in these visualizations. And of course, we can only visualize 3 dimensions. So we have to somehow simplify this complexity, and we use dimensionality reduction techniques to do that. And in the last years, researchers have been using these dimensionality reduction techniques to create 1D plots, then 2D plots, then 3D plots. And for example, one of my favorite papers is this one by Tom Goldstein's team. That is an absolute reference in this area, wonderful paper, and I refer to it very often. And so the Lost Landscape project that I'm speaking about today, what it's trying to do is to bring greater and greater detail to these visualizations and also to study them in movement, the dynamics in movement through the steps and the epochs, and also to bring to them the creative aspect that is not just about making these representations look nice, because a lot of people see them and they say, oh, they look nice, but it's more than that, right? For example, in this example, we can see a picture of a galaxy on the left, and this is the raw picture, and on the right, we see what people typically see, that is the post-produced version. And of course, the one on the right is much more beautiful, but it's more than that, right? It is easier to understand, it is easier to work with, and if we may arrive to a new insight with one of these two, it's probably going to be with the one on the right. So, the creative aspect of the project is more than just about making it look nice. No? It's also about those other things. So we have all of this complexity. And in the last years, also researchers, as we take these dimensionality reduced representations of these weight spaces and we combine them with the loss values and we build these representations, researchers have found connections between the geometry of these surfaces, also using both numerical analysis and visualizations, and different properties of the networks. We all know that when we use Resnets, right, if we use skip connections, we get a smoother surface. And if we, for example, use SGD with small batch sizes, we tend to converge to flatter minima, and this tends to correlate, most researchers agree, with better generalization, which is quite intuitive, because if we are in a minima, in a certain point in weight space, and we move a little bit, and the minima is flatter, as we move, the loss value is not going to change too much, so we kind of have a wider margin of safety, which means that the boundaries that, for example, in classification separate our data, they are going to be more resilient. So we find these type of connections. That's why we're interested in creating these types of visualizations. And so we get to a point in weight space, and we don't want to be blind. We want to understand what happens if we move a little bit. What happens around us? Is the surface rough? Is it smoother? Is it full of non-convexities? What's going on? And we use different mathematical operations, right, to navigate these weight spaces in the high dimensionality. We can do an interpolation from a point in weight space in a random direction, or we can do linear interpolation between 2 points in weight space, or we can pick a couple of random directions that are orthogonal to each other and they make a plane, and we can slice the high dimensionality with it and project it onto the plane and calculate a lot of loss values on a grid on the plane and build this 3D surface. Or we can pick a couple of minimizers, points in weight space, and look for paths that connect these two minima, maintaining a low loss value. And this is a wonderful paper, and I will be talking about this in the examples. So we are exploring all of these cross sections of this hidden beauty, these hidden mysteries in the high dimensionality, and we can do these dimensionality reductions in many different ways. For example, we can use PCA directions, and these are the directions that are the most optimized in the system, down the gradient. And if we do this, we will be able to capture, for example, pretty well the variation in the trajectories, for example, the trajectories of SGD. But we will not capture so well all the richness around in the rest of the landscape, the distribution of non-convexities and convexities, if they exist. Conversely, if we use random directions, for example, we will better be able to capture the richness of the landscape, the distributions of non-convexities and convexities, but we will have more trouble to capture, for example, the variation of the trajectories. Why is this? Because it has been shown that the trajectory, for example, of SGD, right, it exists on a very low dimensional subspace, and if we pick a random direction, because of the counterintuitive properties of high dimensional space, it will probably be orthogonal to the trajectory, and we will not be able to capture well the variation in the trajectory. So in summary, different strategies, different directions serve for different purposes, and we can do these dimensionality reductions in many different ways. Because of the same counterintuitive properties of these high dimensional spaces, when we pick a couple of random directions, it's practically guaranteed that they are going to be orthogonal to each other, because as we know, the higher the dimensionality, the higher the proportion of the space that is being occupied by the orthogonal vectors, and we can use the cosine similarity and basic proofs to demonstrate this. And finally, the last thing that we have to consider very important is that we must normalize these directions, and it's very intuitive to understand why. If we have, for example, a couple of minimizers with different magnitudes in the weights, and we apply the same perturbation of the same magnitude to them, and we build visualizations and we compare them, we're going to see differences that are being caused because of the lack of the right proportions between the perturbation and the magnitudes of these weights. And this can produce different types of issues, like we see in this example from Tom Goldstein's team paper. We can have, for example, a small batch size and large batch size minimizers, and we can apply weighted decay, and of course the updates are going to happen more often in the case of the small batch, so those weights are going to get smaller. And then we build the visualizations, and we see that, for example, a minima that looked flatter now looks sharper, but the generalization is still better. So again, we're seeing the impact of the lack of the right proportions of the perturbation compared to the weights. So we solve this very easily normalizing the directions. We can normalize by layer, by filter. By filter works very well if we have a convnet. If it's not a convnet, we can apply similar thing with the equivalent structure. And that's it. We create these dimensionality reductions, we produce these 3D representations, and then we ask ourselves, so are we capturing in these visualizations useful and actionable data? Do we have there a connection that even if we're so far away is useful enough to work with it? And yes, the researchers have demonstrated that the main curvatures of these dimensionality reduced representations are a weighted average of the curvatures in the high dimensional space. And to demonstrate this, they use numerical analysis, they use the hessian, they use the eigenvalues, the extreme eigenvalues, the ratio of the extreme eigenvalues. They can, for example, build heat maps and study the distribution of non-convexities and convexities in the high dimensional space and compare them and see that they match, and that, for example, if we see non-convexities in these dimensionality reduced representations, it means there will be non-convexities in the high dimensional space. And if we have a positive curvature, if we have convexities, it doesn't mean that in the high dimensional space everything is convex, but it means that the positive curvature is dominant. So in this way, we demonstrate that there is a solid enough connection that allows us to work with these visualizations and to try to chase new insights through them. And then finally, combining different networks and different parameters, these representations get built. And now we get to the dynamics that I haven't spoken so much about in other talks. As we do the same thing, not just in static terms, but also through different steps and epochs, and we build these representations in movement, we begin to see these counterintuitive effects. We see shapes that appear out of nowhere. We see morphology shifts. We see tunneling. Why are these things happening? And we're going to see these things in the examples that I'm going to show later. And for that, we have to accept that in comparison with this big challenge that we have ahead of us in these very, very high dimensional spaces, we live in our own flatland reality. And there is a wonderful talk given by mathematician Matt Parker at the Royal Institution called Four-Dimensional Maths, where he provides these beautiful examples in video, where we see, for example, a 3D cube that is moving through a 2D world. And from the perspective of the 2D world, what we see is this square that appears out of nowhere and eventually disappears. Of course, from the perspective of and here we see the same thing, corner first, and then it gets crazier. We see a triangle that appears, it becomes a different shape, and eventually disappears. From the perspective of the 3D world, everything is continuous, but from the perspective of the 2D world, we see these counterintuitive effects. This is falling edge first, and we see this rectangle that appears out of nowhere. It expands, then it contracts, and then it disappears again. And now we see the same thing, and on the right we can see what would be the perspective from the 2D world, all right? And now we're going to see the simulation of a 4D object falling through a 3D world, and the shapes get even more complex and even crazier. So in the representations of the landscapes in movement, we're going to see a similar dynamic. As we move through the steps and the epochs, every move triggers a dimensionality reduction transformation. And this is analog to filtering that high dimensional space through our low dimensional reality. The high dimensional continuity remains, but those counterintuitive changes are caused by the act of filtering it through our low dimensionality as we progress through that space. And this is what produces these counterintuitive effects that we're going to see in these examples. There is also the noise, because there is morphology noise in the landscapes that, of course, for example, like the skip connections in the Resnets that produce the smoothing effect, they come from the architecture, the hyperparameters, and there is the dynamic noise. And an example is if we use, for example, small batch sizes and we're capturing steps, and of course, in each batch, we're using a different part of the data set. So this is going to produce a variation in the dynamics of the landscape, for example. All right, and we also see in the examples that Matt provides how, as we go higher in dimensionality, these counterintuitive effects, they get more and more complex as well. And in our case, as we go from this billion and soon trillion of dimensions to our 2 dimensions plus the lost 3, we're going to see different counterintuitive things happening that we're going to see in the examples. One of them is tunneling. We may see at the beginning of a training process a landscape that is quite flat, and then as the training progresses, we see how the convexity begins to tunnel down the landscape. And this of course doesn't mean that in the high dimensionality there is like a hole being created. No, of course not. As we know, in the high dimensionality, we're just moving in these millions and billions of different directions. But when we filter that through our flatland reality, we see this counterintuitive tunneling in this case. Now, what is really interesting about this is that we've been worried for a long time about the local minima and the saddle points, etc. But now we are beginning studying this type of dynamics with numerical analysis and with these visualizations. We're starting to go into mode connectivity, finding that it's much easier than we thought to connect the different minima. And we're going into all of this concept of the blessing of dimensionality that, for example, Babak Hassibi explains really well in this wonderful talk, in which he tells us that when we initialize well our networks, the problem of finding a good minima goes from finding a needle in a haystack to exploring a haystack full of needles, because it becomes almost a local problem. And by studying all of these dynamics as well, we're getting closer to understand more and more how the high dimensionality has a lot of blessings that are being revealed little by little. So we're exploring all of these cross sections of this hidden beauty. And in whatever dimensionality we exist, we are encompassing the lower dimensions, we are exploring the cross sections of the higher dimensions. That's why in our 3D reality, we can see these slices of time. If we could live in higher dimensions, above time, maybe we would see time as all at once, right? But we're exploring all of these cross sections and always doing these dimensionality reductions that we can do in many different ways with different strategies, and even adding extra factors to communicate extra informations, but they are all quite similar to each other. And finally, in the creation of these representations, and we are now going to see this 10-minute video, So as I explained, this is a multidisciplinary project in which I am combining a lot of different things, right, that go from the engineering, the programming, the optimization, the modeling, all the, what is the 3D surfaces and the audiovisual, etc., all of the different parts. And now we're gonna see this 10-minute video with examples. So the first one is the learning rate stress test, in which I am basically using different learning rate schedules to to basically study different resiliency ranges in which I modify the learning rates in very radical ways, and I study how the surfaces respond. And we can see how, as you reach different parts of the high dimensionality where the process collapses, this basically transforms into a similar collapse in the dimensionality reduced representation. We can also see the process of tunneling in these examples, how the convexity begins to tunnel down the landscape as well. So we're also using here another learning rate schedule and analyzing these resiliency ranges to see what are the ranges in which we can still take the learning, the training process to a good solution while still doing radical changes in the learning rate. This is now mode connectivity, a wonderful paper, a collaboration with my friends of NYU and MIT, Timur Garipov, Pavel Ismailov, then we have Dmitry Podoprekhin, Dmitry Vetrov, and Andrew Gordon-Wilson. And what these researchers are doing in mode connectivity, right, is they get to, for example, three solutions, three different minima with SGD, and 3 points make a plane, and they take 2 of these points and they rotate this plane through all the high dimensionality until they find a path that links these 2 minima through maybe a Bezier curve or a polygonal path while maintaining a very low loss value. And what is really fascinating in the visualization is that we can see how the barrier that separates with a high loss value the different minima is like melts and disappears gradually as the training progresses, as the algorithm progresses, until the minima are linked. And again, this doesn't mean that in the high dimensionality, the barrier between the minima is disappearing. It means that as we move in these millions and billions of directions in the high dimensionality, as we dimensionality reduce this to our flatland reality, the counterintuitive effect that we see is this barrier melting between the minima. And we see here finally the 2 minima connected, and the straight connection still has a very high loss value, but the Bezier curve connection has this very low loss value of connection. Here we see a static representation in very high resolution where we see the contrast between the rough surface in the high loss value areas and the smoother part that connects the minima. This is a zenithal view of the connection between the minima. This is also a capture of that dramatic contrast in the rough surface in the high loss value areas that are higher than the area that connects the minima, and this very, very dramatic contrast between both these I call the cathedral, another dramatic representation of this contrast between both areas. I see that because of the connection, the playing of the video is struggling a little bit. Okay, these are the studies in which I change different parameters and then I capture specific parts of the landscape to study them as I change different parameters, dropout, etc., etc. And I study very specific parts of the landscape, changing different parameters. This is an example, for example, with Resnets, as we study the morphology and the dynamics, for example, with non-skip connections, with skip connections, and analyzing all the changes in morphology and dynamics. This is the Lost Landscape Library project. This is an ongoing project different from the Explorer app. This is an ongoing project to be able to understand the impact on the surface of many different gradual changes in the parameters of the networks. This is a long-term project. I don't know when it will be finished. This is different to the Explorer app, and this is ongoing at the moment. And yes, this is the Lost Landscape Library project. And now we move to the collaborations with the Landscape Research Deep Learning Group, founded by Diganta Mishra, that has now joined Weights and Biases, so this is very exciting. And we do, for example, here a collaboration to study the lost landscapes of activation functions like Mish, Swish, and ReLU. And basically, in this study, right, we are analyzing the 200th epoch of the training process of a ResNet 20 network, and we are analyzing how well conditioned are these surfaces, what is the quality of their minima, the flatness of their minima, etc., etc. And we are seeing that, for example, Mish has this very well conditioned surface in comparison, for example, with ReLU, and the quality of the minima, the flatness of the minima is really nice, etc., etc. And we do these types of collaborations that we are expanding in different directions. All right. Lottery Garden, this is regarding the paper by Jonathan Frankel and Michael Carvin, the lottery ticket hypothesis, and I am pruning gradually the network, pruning the smallest weights first, and as I prune the networks throughout 6 epochs, I represent the lost landscapes, and it's really fascinating, but because we consider up to 40-50%, the performance can even exceed the performance of the fully trained network, and the landscapes are really, really well conditioned. And only when we get to 80 or 90%, the process begins to collapse. This is when they break through these planes. They are going beyond the performance of the fully trained network. And we can see, therefore, that indeed there is a subset of the weights that are responsible for most of the performance of the fully trained network. And we can see that the landscape is really well behaved until we reach the 80s or the 90%. And here we can see 20%, how we exceed the performance of the fully trained network sometimes throughout the 6 epochs, right? And as we approach 60-70%, we see that this tunneling process begins to be unable to reach as low until eventually we get to a part in the high dimensional space that collapses completely the transformation. Edge horizon and downfall, as I do these experiments, I give names to different parts that I'm interested in. So I call the edge horizon the transition to the main convexity of the landscape, and the downfall, the transition from the edge horizon to the bottom of the minima. And then, of course, we have the minima, etc., etc. And when I do these studies, this is an interesting paper because it tells us, for example, that we used to think that batch norm was correlated with a smoother surface, but then they say, oh, but when we do a different combination of, for example, of depths, etc., we see something different. And this is the same thing that I have found in many of my experiments. It takes a lot of time because sometimes you get some correlation, but then with a different combination of parameters, it goes in a different direction, etc. Okay, this is a very high resolution representation of an edge horizon, the approach to an edge horizon, and using also the creative aspect of the project to make it easier to understand the morphology. This is a slow process of tunneling. That ball represents the minimizer. This is a transition from the top of an edge horizon to the bottom below the minima to study the minima from below. It's a pity that because of the connection, I think it's because I'm also recording it, is struggling the video. But we can mount this afterwards. Okay, this is also a flyby on top of an edge horizon. And this is one of my favorites. This is one of the first ones I created. This is also the beginning of one of these tunneling processes. It's one of my favorites because it's also one of the first ones I produced. All right, and now we are moving. Okay, this is another static representation of an edge horizon. This is a high resolution capture of a downfall, and we have other representations of edge horizons as well in here. All right, where are we going now? Dropout. Yeah, dropout. As we begin to add, during the training process, of course, dropout to the networks, this homogeneous layer of noise begins to take over the landscape. And of course, this is a layer of noise that is disruptive enough to prevent too much overfitting and too much memorization of the paths throughout weight space, but not disruptive enough to prevent the network from reaching a good solution. Unless we go too crazy with the dropout, and then of course we will, make impossible the movements in weight space. So yeah, and we see here the representation in movement as we crank up the dropout, and this layer of noise begins to take over the landscape. Fascinating. So that is the dropout. And now we're going to move to Bayesian deep learning, dealing with uncertainty so that we don't do overconfident predictions. And this is the group of researchers with Wesley Maddox, Timur Garipov, Pavel Ismailov, Dmitry Vetrov, and Andrew Gordon-Wilson. And of course, they want to build a probability distribution of the weights of the network that they call the posterior, right? But this is intractable, so they approximate it through the trajectory of SGD. So what they do is they get to a good solution in SGD, and then they put a high learning rate, and they explore all around, and they get to different solutions that explain the training data but do different predictions on the test data, and they build a Gaussian distribution with those, and they demonstrate that that Gaussian distribution explains the geometry of the loss surface well. And in this collaboration, we are representing the actual proper loss landscape built with the real data and the exact position of the solutions and also of the Gaussian distribution as well. This was presented in NeurIPS 2019. The previous paper was of NeurIPS 2018. Okay, and now we go to, I think we're going to go to the GANs. Yes, the wild networks. So we all know what is the problem with the GANs. That is that the loss function does not correlate well with the performance, for example, of the generator of the generator or the quality of the images that it produces. But if we use a different type of loss function, like for example the Wasserstein, a different type of GAN, the Wasserstein GAN with a different type of loss function that uses the Wasserstein distance, the shortest distance to move a probability mass from distribution to another, then yes, that type of loss function correlates much better with the performance of the generator, and then we can study better the dynamics of the loss surface of a generator, and we can see this more unpredictable dynamics. We can really see that these networks are so much harder to control, so much harder to tame as we study the dynamics, for example, of the surfaces of the generator. And this is a project with a Neural Concept, Swiss company, about geometric deep learning. This is not loss landscape, it's just to show you that the project is also branching in different directions. And this is basically predicting the aerodynamic properties of a drone, the pressure exerted by the air on the surface of the drone. And we can also visualize the features being learned by the filters, which in a normal ConvNet, we would visualize with a 2D image, but in a geometric 3D ConvNet, we can map on top of the surface. And finally, to end this presentation, this is the Loss Landscape Explorer app that I just launched a few days ago. And this is an app where you can explore different loss landscapes created with this dimensionality reduced techniques and with real data, and you can navigate them in 3D, and you have different features, like for example this auto descent mode. You can click anywhere on the landscape to begin a sort of descent through the gradients or the subgradients as you like. And of course this is not doing a gradient descent in the high dimensional space, all right? This is a gradient descent through the dimensionality reduced representation, but it can be useful for educational purposes and also to reflect on different research aspects. For example, it's very fun that you can do one of these descents and you can see that it gets trapped in some part of the landscape in a local minima, and then you have a descent rate control that you can manipulate in real time, and then you can crank it up and help it escape that local minima and continue moving down, or you can get to a good minima and then you can, the gradient gets almost zero, but then you crank up the learning rate at the bottom of the minima, and then you explore the minima and get to other solutions, which is what the Bayesian friends are doing, for example. So, you can reflect on different research aspects and use it for educational purposes. And I will be adding more features over time to this tool. And you can also capture different views of the landscapes, in PNGs, etc., etc. There are other features. And this can be accessed for free, completely open. And you don't have to install anything. I programmed this in JavaScript. This is using React. This is using WebGL technology. And it can be installed. This is a progressive web app, so it can be installed anywhere. It doesn't require logging or register or anything. And I will be adding more features to it over time. And this can be accessed at losslandscape.com/explorer. And that's it. That concludes the presentation. And if you want to explore more of my work, you can go to ideami.com. And that's it. Thank you very much.